So this is just a little refresher for you. I want to make sure you guys are feeling comfortable with these. At this point you should be. If you're not, feel free to come see me. Yada yada. Technetium. X marks the spot, that's where I'm going. Technetium is in the 1, 2, 3, 4, 5th row. It's in the D block. Since it's in the 5th row D block, it means N is equal to the row minus 1, which means I'm looking at 4D, and I'm going 2, 3, 4, 5 in, so 4D, 5 is my stopping point. So we're going to go all the way through until we get to 4D, 5. So the orbitals, remember it's the dashes with the arrows. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4D. Okay, so everything's full until I get to the 4D. So all of this is full. Go ahead and fill it up. These are your favorites, aren't they?
You love them so much?
Everybody likes the pattern, but they hate doing these. It's kind of like, you know, math when you have 20 homework problems and after 5, you know you got to master. But then you have to keep doing them. All right, so 4D5. 4D5, this is where everything changes. You have to remember the rules. Okay, Hund's rule is very important here. So whenever we look at Hund's rule, each orbital of a subshell will receive 1 electron before it receives another. Warning to you, those 3 rules, make sure you know them. So I have 5, so 1, 2, 3, 4, 5. And that's it. Any questions on that? Because this is like the last one I'm doing. We're churning to a new lift today. Today we go into what I like to go into. Nothing. So the electron configuration does away with the arrows and the dots. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d5. Noble gas configuration, we substitute in our starting point. We change that up. So we sub in. So we put our finger on technetium. We go up a row and all the way to the 18th column. The last noble gas we crossed was krypton. So we have to put krypton in square brackets. Something to note, it must be square brackets. The first letter must be capitalized, the second letter must be lowercase. That is always true for the chemical symbols. So now, that substitutes all the way in for the last thing we hit. So it subs all the way to here. So from 1s2 to 4p6 is all substituted in by krypton. Now, I start the 5th row, so 5s2, 4d5. Any questions?
How do you know on the orbital to go up at the end? Like the up arrows?
So you always start with the up arrows. So I'm going to erase these so I can try and explain. So when you look at it, how many orbitals are in a D subshell? So how many dashes does it have? It's got 5. So you got the 5 dashes. Now you look at how far you've went in. So in this case, I went 5 in, which means I have 5 electrons I have to show. So to do that, I go to 4D, and I always give each one an up arrow first. So I do 1, 2, 3, 4, 5. That's it. I'm all out. That's just, there's no down arrows now. If I went farther in, then I would come back in and get the down arrows. Makes sense?
I guess there's 10 arrows in total because there's 10 blocks. 8D, 5 in, so you're only going to need 5 electrons. You don't need the whole 10. You're not going through here. Just when you go up before you go down. It's true.
I like that. Does that help? Okay. All right. I came up with a way of actually getting you to understand percent error and not make a mistake, and I decided to not simplify it. But I think I'm gonna hold off on percent error until everybody else comes back, because there's tons of confusion on that, and that's 100% my fault. Which just means we're just gonna go to something confusing, because now we get to the really hard part of the unit we want to get to. So, if I mentioned something to you, you would be able to describe it to me. I hope you would. So if I talk to you about this concept, so wave-particle duality. What is wave-particle duality?
Light is a wave.
So light being a wave and a particle. So another way of saying this is, besides light, is electromagnetic radiation. I feel like it takes forever to write that word. Is both a wave and a particle. Whenever we talked about this, one thing we talked about was what proved these things. So if I want to talk about electromagnetic radiation being a wave, what proved electromagnetic radiation as a wave? Double slit experiment. So you guys remember double slit experiment, yeah? Okay. What about for it being a particle?
The one where they hit the metal with certain types of electromagnetic
Okay.
radiation.
So they hit it with, what happened?
The electrons bounce off.
So the electrons are popping off. But wait, what's an electron? It's a particle. But a wave interfered with a particle, which made Albert Einstein look and say, with the photoelectric effect, that clearly electrons are particles, which means that particles interfere with particles, waves don't interfere with particles, so that results in a meaning that electromagnetic radiation has to actually also be a particle. Quite simple, right? I would be totally wrong. Did you get your hair cut?
This is just my natural hair.
Oh, okay. It just looks different. It looks nice. Just looks different. I know how women feel if they go get the haircut and nobody notices. So. make sure. So electromagnetic radiation has wave-particle duality. It's interesting. So there's a guy that just asked a question. Just a random question. I'll give you his name. I'm not caught up on the name if you haven't figured that part out. But he's French. Louis de Broglie. I think I said that right. If I didn't, well, he ain't gonna worry about me. Louis de Broglie. That's my best French accent. Louis. He asked a simple question. If light has wave-particle duality, why not an electron?
Whoever has Crystal Thomas's class, please call the office.
So, it's a weird question to ask. You agree? 'Cause what is an electron?
Negative charge particle.
Negative charge subatomic particle. Very weird question to ask. So, came up with even a weirder thing. They probably decided to take a piece of foil, very thin piece of foil, and shine X-rays on it. That's what I thought too. So he does this, and he is shocked with what he sees. He's seeing an interference pattern where electrons should be. Well, what's interference patterns a key for? Isn't that the quality of waves? This is the part where you shake your heads, yes.
Yeah.
There we go. So interference patterns are qualities of waves. So what does that mean for the electron?
Oh.
That the electron is a wave nanoparticle? So this is where the world gets freaky and weird for you. Because we have an experiment, you're very familiar with it, that we can do to prove whether something is a wave or a particle. Ah, right there. So guess what scientists decided to do?
They're always doing silly stuff.
But the hall told you it would come back to the class. They looked and said, you know what? Let's do the double slit experiment. It proved a lot of things. Bum, bum, bum. Welcome back. Double slit experiment. Only this time, comes back with a vengeance. So double slit experiment. If you don't remember the setup, don't worry. Mr. Hall's here to help you. So we have a box that emits out whatever source we want. Remember, we're not looking at electromagnetic radiation anymore. What are we looking at?
Electrons.
Electrons. So, here are electrons. It's going to get released out. So an electron emitting device. Just call it that. And there's a hole for the electrons to come out. Then comes the fun part. We have the wall. Remember the name of the experiment? Double slit. So we need 2 slits. You know what we need on the back?
Another wall.
It has a detector on it. That's going to detect what happens. Now, what do you expect to see? What is an electron?
Subatomic particle.
It's a negatively charged subatomic particle. So what do you expect to see?
At least particle.
A particle? So on the back wall, on the detector, what type of pattern do you think I should see here? Interference. What do you think we should see? Just 2 bands. This is the equivalent as if I had 2 holes in a wall and I was sending bowling balls through them and they hit the back wall. What do you think would happen in the back wall? I would see the area where the bowling balls are hitting the wall in 2 spots, or I'm going to see a whole bunch of spots? 2 spots. So what you expect? Guess what scientists expect? It's a stinking negatively charged subatomic particle. We're going to see 2 stupid bands. Then they ran the experiment. Turned the electrons on. They went and got a cup of coffee. They're like, hey, yo, you know, bada bing, bada boom. You watched that game last night? Yeah, man. They turn over, they look, they go, sweet bejesus. Is that 2 bands?
No.
What type of pattern is that?
Waves.
It's quality of waves, it's an interference pattern. Should I see that?
No.
No! You should not see this! What are electrons?
Particles.
They're particles! Why am I seeing an interference pattern?
There's something wrong with it.
You know what? You're smart. Something is wrong. That's what they thought of it. Electrons are very small. You know what? We're sending these things out. We're not controlling the rate they're coming out. They're spitting these things out super quick. So he said, hold everything. Here's what's happening. These electrons are just coming out, and they're coming out so fast and too quickly. They're interfering with themselves and bouncing all the way around. So we have to fix this. So now they change it, and they say only 1 electron at a time. Thank God scientists are smart, right? Because you know what happens is they do this, and scientists are really smart, really intelligent people. So they do this, they go get a cup of coffee, they're talking, yada yada, and you know they're like, yeah man, this is totally gonna fix this thing. They come back, they look at it, and they get the 2 bands on the wall. So there's the thing that comes in. Holy smokes! What is that?
Wave interference.
What's an electron?
Particle.
Why in the world are we getting an interference pattern with particles? It makes no sense. What? One electron at a time. It's impossible. The electron can't interfere with itself. Scientists are smart though, right? Here's the fun one. So they're like, you know what? You little stinking buggers. I got your number. We're going to figure you out. Here's what they did. They decided, Forget this. They went to one of the slits and set a detector. Why would they set the detector at one of the slits?
To see what's happening when they go through.
Exactly. So now I can see the electron comes through this slit or it goes through that slit, right? That's the only options here. That's it, right? Am I wrong? Is there another option here? Because I'm confused. There's only two slits, so you're only going through that one or that one, right? So they do this, and you know what happens, right? So now they're going to figure it out. They're the mad scientists. They're like, man, we're geniuses. We're going to figure this thing out. You know, it clearly has to be going. But we're going to figure out why there's an interference pattern going on here. And they set the detector, and then they look back at it, and they're like, okay, so let's look at the interference pattern. Is that an interference pattern?
No.
What's the two bands equality of?
Particles.
But electrons gave me interference patterns, right?
Mhm.
But now I have two bands. What the world? Do not be scared.
How do you do that?
I'm still confused to this day, and I teach this mess. Weirdest thing on the face of the planet happened. They ran this test time and time and time and time again. It didn't matter. No matter what they did, they could run it 1,000 times. If the detector was present to where we were observing the electrons, we got this pattern. If I removed the detector, guess what we got?
Wave interference.
We got an interference pattern. What are interference patterns qualities of?
Waves.
Waves. But what's an electron?
Particle.
No.
So,
Braugel had the idea. Interference pattern is a quality of waves. Particles cannot do this. So what does this mean for the electron? Double slit experiment. Proved electrons to be waves and particles. If you observe then acts like a particle. Don't observe, acts like a wave. This totally changed the world of science as we know it. This experiment wrecked the foundation of what we knew as science. At the time before this experiment was done, we thought we almost understood everything of physics. There's just a couple little cracks, little slivers and stuff. It's like we're not quite sure about. But as soon as we go in and do the double slit experiment, you cannot deny the evidence. The electron has wave-particle duality. With the wave-particle duality of that electron, open the whole world up for us. So let's all pretend we're all like super intelligent in here, okay? I know that's not hard for you because you are super smart. Okay. Just pretend I am on your level, all right? So, we're all doing experiments. Let's say 3 of us need the electron to be a particle. 4 of us need the electron to be a wave. What do you think we need to do? Nothing. Leave it alone. Don't touch it. You just look and say, I'm going to do my experiment. The electron will be a particle. Well, how do you know that? Because it's a particle. If you need it to be a wave, that's what you do. Leave the stinking thing alone. It'll be a wave, man. No? Don't mess with it. You look at it and say, hey, you do you, boo-boo. It'll act how you need it to act. The key is you leave it alone. The detector that they were using messed with it, so it went back to acting how it's supposed to act.
He's just nervous.
That's what it is.
He's shy. He doesn't want to be found out as a wave.
It's like, oh no, they figured me out all these years. Nobody knew. This opened up something for us. This opened up the world of quantum. You may have heard a little bit about it, but not a ton. When you break it down and you look at it, the quantum realm, the quantum world is all based off of this, that the electron has wave-particle duality. Which brings us to the ideas of the quantum world. Whoa. Now, before I give you the first one we're going to talk about, it's maybe the only one we get to talk about today, we need to address something in the room. Number one, we're not going to talk about it. Not the concept, but the name. You're going to find out why when I give you the name. This is where he got his name from. If you have no idea what I'm talking about, thank God. They've watched the show. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle really breaks us into the quantum world. Because Heisenberg's uncertainty principle states something. It is impossible to determine an electron's position and velocity at the same time. Here's the reason as to why. To find out one, you have to affect the other. So to find the one, must affect the other. Here's the way I like to explain it. You're tasked with a very simple task. You're in a room, and there's a bowling ball traveling around the room. But the walls are soundproof, and the floor is soundproof, so you don't hear the bowling ball hitting the wall or anything. You have bowling balls. Your job is to take your bowling ball, roll it, and hit the other bowling ball, so that we can find the bowling ball's location. Oh, I forgot to add something. The room is pitch black and you can't see anything. You have no idea where it's at. So what you do is you start yeeting that bowling ball through there. Eventually there comes a point that you hear clack! What was the clack noise? Hitting the other bowling ball. So question to you, do I know where the position of the bowling ball is?
Roughly.
I love the fact that you answered it like that. We have an idea of where it is. Why do we have an idea of where it is? What happens after I hit it with my bowling ball? Is it at that same point anymore? No, it moved. So now I have an idea of where the position of it is. Can I know the velocity of it? And how fast it's traveling? No, because what happened when I hit it with the bowling ball? I jacked that thing up. It's done. You can't know both for the electron. You know one or you know the other, but you cannot know both of them. I know today may have been confusing, and you may walk out here a little confused. That's okay. I've been teaching this for 7 years now. It's still confusing. But you can't argue that. So have a great, wonderful rest of your day, everybody. You know, be inspired. Make sure and share with everybody the double slit experiment. Explain to somebody the wave particle duality of a particle called an electron.
I always knew there was something wrong with electrons.
Exactly.
They were never protons or neutrons.